The journey inward through Jupiter's system reveals moons like pearls scattered across an ocean of darkness, each one catching the distant sunlight differently. Callisto appears first, heavily cratered and ancient. Then Ganymede with its mix of old and young terrain, visible even from far away. Europa glows with an icy smoothness that hints at the ocean hidden beneath its frozen shell, a world of subtle colors and quiet mystery. But as the innermost of the four great moons comes into view, something entirely different appears. Something that looks like no other world we know. Io fills your window now, and the first impression is of color so vivid, it seems almost artificial. A palette that belongs in dreams rather than reality. Yellows and oranges dominate the visible surface, interrupted by patches of red, white, and black scattered across the globe without obvious pattern. The surface looks painted rather than geological, as if someone had spilled pigments across a sphere and let them dry wherever they landed. This is the most volcanically active body in the entire solar system, a world where the geology never rests and the surface never grows old. You are listening to the Drowsy Astronaut, and tonight we are exploring a moon that turns itself inside out every few thousand years through constant volcanic activity. This is a slow journey, unhurried and calm, designed for late-night listening when the mind is ready to wander and rest, and perhaps drift into sleep. If this detailed exploration helps you unwind, consider leaving a like or subscribing, and do let us know in the comments where you are listening from tonight. Io awaits us now, patient and burning, and we have all the time we need to explore this remarkable world together. As your spacecraft approaches Io, it reveals details that photographs have shown but cannot fully capture. The texture of a world unlike any other, becoming clearer with each passing moment. The lack of impact craters is the first truly strange observation, an absence that speaks louder than any presence could in understanding what kind of world this is. Every other solid body in the solar system shows the accumulated scars of cosmic bombardment. Craters overlapping craters in testimony to billions of years of impacts from debris. Io shows none of this history, its surface too young, too constantly renewed, too freshly made to bear the marks of time. The colors become more complex as the view sharpens, revealing that what appeared as solid patches are actually gradients and mixtures of many hues blending together. Bright yellows give way to oranges that deepen toward red near certain features, while white patches interrupt the warm palette with frost that seems out of place on a volcanic world. Black streaks cross the terrain in some regions, dark material that appears fresh and unweathered, cutting through older deposits like new paint over old canvas. Every color tells a story of temperature and chemistry, of material erupted from below and deposited above in patterns that change faster than human civilizations rise and fall. The scale of the features becomes apparent as familiar reference points fail to provide useful comparisons for what exists on this transformed surface. Volcanic vents dot the landscape, some small and isolated, others clustered in groups that suggest related plumbing systems beneath the visible crust connecting them. Dark calderas, Circular or irregular depressions marking volcanic centers appear scattered across every visible region of the globe in remarkable density. There are over 400 active volcanoes identified on Io, more than exist on any other body we have observed, a concentration of geological activity that defies easy explanation. The surface temperature varies more dramatically here than almost anywhere else in the solar system, a world of extremes existing side by side. Background temperatures away from volcanic activity hover around -130 degrees Celsius, cold enough that oxygen would freeze solid if any existed here. Near active vents, temperatures spike to over 1600 degrees Celsius, hotter than any volcanic eruption ever measured on Earth, hot enough to melt many rocks completely. Between these extremes, every intermediate temperature exists somewhere on this surface, creating a thermal patchwork as complex as the visual one. The white patches that interrupt the warmer colors are sulfur dioxide frost, a compound that freezes out of the thin atmosphere onto the cold ground between eruptions. This frost coats much of the surface away from active volcanic centers, a thin layer that sublimates and reforms constantly as conditions change. The frost appears brightest where temperatures are lowest, where no recent volcanic activity has deposited warmer material over the cold, sublimate layer beneath. It gives parts of Io an almost wintry appearance, despite the fact that this world produces more volcanic heat than any other body we have found. The darker materials tell a different story, representing fresh volcanic deposits that have not yet been coated by the ever-present sulfur chemistry that colors everything eventually. These dark flows are silicate lava, true molten rock similar to what erupts from Hawaiian volcanoes or Icelandic fissures on Earth, though far hotter here than any Earth eruption manages to achieve. Fresh flows appear black or very dark grey, their surfaces still retaining the color of recently solidified magma before sulfur compounds begin their coating work above. Over time, these dark flows will be covered by lighter material, buried under deposits from plumes and nearby eruptions, disappearing into the geological cycle that erases all surface history eventually. The red and orange areas indicate sulfur in various states, heated to different temperatures during eruption and then cooled in ways that preserve particular colors permanently. Sulfur is an unusual element that changes color depending on its temperature history, creating a natural palette that paints Io in hues found nowhere else. The brightest reds often surround active volcanic centers, indicating sulfur that was extremely hot during deposition and has retained that color memory since cooling. Orange and yellow sulfurs were heated less intensely, their colors recording a gentler thermal past, even as they now sit equally cold beneath the distant sun. The first glimpse of an actual volcanic center comes into focus as the view settles on a region where activity is clearly ongoing at this very moment. A dark caldera sits at the center of a complex of related features, its floor visibly different in color and texture from the surrounding terrain. Around this caldera, concentric rings of color spread outward like ripples frozen in place. Deposits from countless eruptions accumulating in layers over time. The innermost rings are darker, representing more recent and hotter material, while the outer rings fade through orange to yellow to the general background color of the surrounding plains. The terrain between volcanic centers shows its own complexity, not merely a passive surface waiting to be buried, but an active participant in the geological processes reshaping everything constantly. Small mounds and ridges suggest buried flows and collapsed features, terrain that has been built up and broken down repeatedly over geological time, measured in thousands of years rather than millions. Fractures cross some areas, cracks in the surface, where stresses from below have broken through the overlying material to create lines of weakness. Even where no active volcanism is immediately visible, the surface bears the marks of a world that never truly rests anywhere. The horizon curves more sharply than Earth's horizon would, Io being roughly the same size as our moon, and therefore wrapping its surface more tightly around its smaller volume. From the surface, if you could stand there, protected from the radiation and vacuum, you would see this curvature clearly, the world dropping away in all directions faster than Earth-trained eyes expect. The curvature affects how features appear from different angles, bringing the horizon closer, making distant volcanic plumes visible from farther away than they would be on a larger world. This is an intimate world despite its violent activity, small enough that its entirety could be grasped from a single extended observation period. The view settles here, hovering over this painted world that looks too vivid to be real, too active to be stable, too young to have been here for 4.5 billion years. Yet Io has been here since the solar system formed, undergoing this constant volcanic renewal throughout the entire history of life on Earth and before. The fires that burn here today have been burning since before our sun finished forming, since before the late heavy bombardment cratered the inner solar system with debris from gravitational reshuffling. This is not a young world in cosmic terms, but a world that keeps itself young through endless activity, erasing its own history faster than history can accumulate. The details invite closer examination, specific features that reveal the mechanics of how Io maintains this remarkable state of constant renewal and transformation. Among these features, certain volcanoes have become famous through decades of observation, their activity monitored by every spacecraft that has visited the Jupiter system since Voyager. One such volcano stands out, even from distance, marked by an enormous red ring that spreads across the surface like a target painted around its central vent. This is Pele, one of the most powerful and persistent volcanic centers on Io, a feature that has been continuously active through every observation opportunity and will serve as our first close destination. The red ring of Pele becomes visible from considerable distance, a circular deposit of sulfur compounds that spreads across an area larger than the entire state of Texas on Earth. The ring surrounds a dark central caldera where the actual volcanic activity occurs, the source of all the material that has been thrown outward to create this enormous colored feature over time. The name comes from the Hawaiian goddess of volcanoes, a fitting tribute for a feature that represents volcanic power on a scale that Hawaiian volcanoes cannot approach, despite their shared divine patroness. Pele has been active through every observation period since Voyager 1 flew past in March of 1979. A permanent furnace that shows no signs of cooling or quieting. The approach to Pele reveals the structure of the central caldera more clearly, a depression roughly 30 kilometers wide and perhaps several hundred meters deep. The caldera floor shows evidence of active lava, areas that glow in infrared observations and appear darker in visible light than the surrounding cooled material, indicating fresh molten rock exposed to space. The walls of the caldera show layers of accumulated material, deposits from countless eruptions stacked one atop another in a geological record that might span thousands of years of activity if it could be read directly. The edges are sharp in some places and eroded in others, suggesting ongoing collapse and reformation as the volcano continues its endless work beneath. The temperatures measured at Pele exceed 1600 degrees Celsius in the hottest regions near the active vents within the caldera floor. This is hotter than any volcanic eruption ever recorded on Earth, where even the hottest lavas rarely exceed 1200 degrees under normal circumstances today. The extreme temperatures suggest that Pele erupts silicate lava rather than pure sulfur, true molten rock heated to extraordinary temperatures by the forces operating within Io's interior constantly. This type of lava, called ultramafic because of its chemical composition, was common on Earth only during the planet's earliest history, when the interior was hotter and such eruptions were possible. The red ring itself deserves extended attention, a feature so large and so distinctive that it serves as a landmark visible from across the entire hemisphere where Pele resides. The color comes from sulfur compounds that have been altered by the extreme heat of eruption, their molecular structures changed in ways that preserve a red appearance even after cooling. When material erupts from Pele, it is thrown high above the surface in a plume that we will explore later, then falls back across an enormous area in all directions from the vent. The accumulated deposits from millions of these eruption events have built the red ring over time, a geological feature created by aerial deposition rather than surface flows. Moving closer to the caldera edge, the surface texture becomes visible in detail that orbital views cannot provide with the same immediacy and presence. The rock here is not uniform but layered, different colored materials stacked in thin sheets that represent individual eruption deposits accumulated over the lifetime of this volcanic center. Some layers are darker, indicating periods when lava flows covered this area directly, while others are lighter, suggesting times when plume fallout dominated the deposition pattern here. The layers tilt slightly toward the caldera center, evidence of the gradual collapse that has shaped this feature as material is removed from below and the surface settles to fill the void. The active area within the caldera draws attention even without instruments to measure its temperature directly. The color and texture speaking clearly of ongoing processes at work. Dark patches mark where fresh lava has recently surfaced. The material still hot enough that it has not yet accumulated the sulfur coating that will eventually make it match the surrounding older terrain. Cracks in the cooler surface crust allow glimpses of the molten material beneath, glowing lines that trace the pattern of convection cells in the lava lake that occupies part of the caldera floor here. The activity is continuous, not episodic, a permanent feature of this location that has persisted through all recorded observation and presumably long before any spacecraft arrived to notice. The plume from Pele rises approximately 300 kilometers above the surface, an umbrella-shaped fountain of gas and particles that extends into the space above Io with graceful symmetry. This plume is visible when spacecraft approach, at angles that allow the material to catch sunlight against the dark background of space beyond. The particles that make up the plume are small, driven upward by the violence of eruption, then following ballistic paths back toward the surface, in gentle arcs that create the umbrella shape characteristic of Ionian volcanic plumes. The material in the plume includes sulfur dioxide gas and sulfur particles, along with silicate fragments, a mix that deposits across the enormous area marked by the red ring upon falling back. The persistence of Pele's activity sets it apart from most volcanoes on Earth, where eruptions are typically episodic events separated by years or decades of quiet dormancy. Pele shows no quiet periods in any observation record, no dormant phases where the volcano rests before resuming activity with renewed vigor. The fires have burned continuously for at least 45 years of human observation, and, presumably, for much longer before our spacecraft arrived to witness them directly. The energy source driving this permanent activity lies not within Io itself, but in the gravitational relationship with Jupiter that we will explore later, a power source that cannot be exhausted through eruption. The area surrounding Pele shows the effects of proximity to such a powerful volcanic center. The terrain shaped by fallout and flows that extend far beyond the caldera itself. Older lava flows cross the landscape in sinuous paths, their original courses still traceable despite the covering of sulfur deposits that has accumulated since they last flowed with molten material. Small vents and secondary features cluster near the main caldera, perhaps connected to the same magma source beneath, but expressing themselves as separate surface features with their own patterns of activity. The influence of Pele extends for hundreds of kilometers in all directions, making this region one of the most volcanically dominated landscapes anywhere in the solar system. The deposits nearest the caldera rim are thickest and most complexly layered, representing the area that receives the most frequent and most abundant deposition from eruption activity overhead. Walking here, if such a thing were possible, would mean crossing terrain built entirely from accumulated volcanic materials. Nothing visible that did not originate from eruption within geologically recent time. The ground would be uneven, small ridges and hollows created by the irregular deposition of plume material falling from above during different eruption events. Each step would cross material that might be only decades or centuries old, a surface so young that human history would be ancient by comparison. The color gradient becomes most apparent when viewing the entire Pele region from above. The darkest reds nearest the caldera giving way to lighter reds, then oranges, then the yellows of the general background terrain at the outer edges of the deposit ring. This gradient records temperature history. The material nearest the vent was hottest when deposited and has retained the deepest red color as a permanent memory of that thermal extreme. Further from the source, material has cooled more before landing, arriving at temperatures that produce lighter colors in the sulfur chemistry that dominates Io's palette. The ring is a frozen thermal map, recording in color what instruments would measure in degrees. The shadow of Pele's plume sometimes falls across the surrounding terrain when the geometry of sunlight and eruption aligns, a temporary darkness that sweeps over the surface as particles block the sun. These shadows are visible in some spacecraft images, ephemeral features that last only moments before shifting as the plume dynamics change, or the viewing angle evolves during flyby trajectories. The shadows confirm the reality of the plume, even when the plume itself is not directly visible. A reminder that material is constantly being thrown above this world and falling back in patterns that reshape the surface continuously. The shadow passes, but the activity that casts it never stops. The overall impression of Pele is of contained violence, enormous energy expressed through features that seem almost peaceful when viewed from distance, despite the extreme processes creating them. The red ring could almost be decorative, the plume almost graceful, the caldera almost serene, when not considered in terms of the temperatures and forces involved. This is the nature of Io's volcanism, beautiful from a distance, terrible up close, continuous in ways that make Earth's volcanoes seem mild and intermittent by comparison. Pele is not the largest volcanic feature on Io, nor the most powerful in terms of raw heat output, but it represents the character of this world, as well as any single location can. The examination of Pele could continue indefinitely, new details emerging at every scale of observation, from the global to the microscopic, but other features await exploration as well. The plumes themselves deserve extended attention, these fountains of material that rise far above the surface and create the deposits we have been observing from ground-level perspective. The mechanics of how material is thrown so high in Io's weak gravity, and what happens to it after it leaves the volcanic vent, tells us much about this world's nature. The umbrella shapes and the gentle arcs of falling particles create some of the most visually striking phenomena anywhere in the solar system. Silent eruptions painting the space above a colorful moon. The plumes rising above Io's volcanic vents create some of the most visually spectacular phenomena anywhere in our solar system. Fountains of material reaching heights that dwarf anything possible on Earth. When Voyager 1 flew past Io in March of 1979, the cameras captured images that stunned scientists who had expected to find a cold, cratered world similar to other moons. Instead, the images showed umbrella-shaped fountains rising from the surface, material being thrown hundreds of kilometers into the space above this small moon. That discovery changed everything we thought we knew about what moons could do, revealing a world more geologically active than Earth itself. The tallest plumes on Io reach heights of 400 to 500 kilometers, rising so high that they extend well beyond the thickness of any atmosphere and into what amounts to open space. For comparison, the International Space Station orbits Earth at about 400 kilometers altitude. So these plumes reach heights that would put them in low orbit around our planet, if they occurred there. The material rises because it is ejected at tremendous velocity from the volcanic vents below, driven upward by gas expansion and eruption pressure before gravity eventually pulls it back down. The velocities involved are approximately 1 kilometer per second, fast enough to reach these extreme heights before the arc of the trajectory begins its downward curve. Io's gravity is weak compared to Earth's, only about 18% of what we experience on our home planet's surface. And this weakness allows the plumes to reach heights impossible anywhere on Earth. On our planet, even the most violent volcanic eruptions rarely throw material higher than perhaps 40 or 50 kilometers at most, in extreme cases. The combination of violent eruption velocity and weak gravitational pull creates the conditions for these soaring fountains that define Io's appearance from space. The physics is straightforward once the conditions are understood, but the results are extraordinary by any standard of comparison. The umbrella shape that characterizes Io's plumes results from particles following ballistic paths after leaving the volcanic vent. Physics made visible in the geometry of these silent eruptions. Material leaves the vent, traveling upward and outward, rising along curved paths that reach maximum height before arcing back toward the surface below. Because particles are ejected in all directions from the central vent, the combined paths create a symmetric shape that spreads outward at the top before converging back toward the ground. The umbrella appears most clearly from viewing angles that silhouette the plume against the darkness of space or the illuminated surface below it. The silence of these eruptions deserves reflection, a fundamental difference from how we experience volcanic activity on Earth, where sound is often the most terrifying aspect. On Earth, volcanic eruptions produce tremendous noise, explosions and roars that can be heard for many kilometers, and that trigger primal fear responses in animals that hear them. Io has almost no atmosphere to carry sound, meaning that even the most violent eruptions occur in absolute silence. No roar accompanying the fountains that reach into space. An observer near an erupting vent would see the material rising in complete quiet, an experience of violence without its usual auditory accompaniment. The material within the plumes varies, depending on the type of volcanic activity producing them, with two main categories observed through decades of spacecraft observation and study. Some plumes are sulfur dioxide driven, smaller fountains perhaps 100 kilometers high that are powered by the vaporization of frozen sulfur dioxide near volcanic heat sources. These plumes are relatively common and produce deposits of white or pale yellow material in rings around their source vents across Io's surface. The larger plumes, like those from Pele, involve silicate magma and reach much greater heights, producing the colorful deposits that mark the most powerful volcanic centers on this moon. The fallout from plume eruptions creates the rings of deposited material that we observed around Pele and that surround other major volcanic features across Io's surface. As particles fall back toward the ground, they spread across an area proportional to the height they reached and the initial velocity that carried them upward from the vent. The deposits accumulate over time, building the thick layers of volcanic material that constitute Io's surface and burying any previous terrain features beneath fresh material constantly. The process is ongoing, never pausing, as active plumes continuously supply new material to the surrounding regions at rates that make geological change visible over human timescales. The observation of plumes has become a standard part of every spacecraft encounter with the Jupiter system. Scientists eagerly examining images for evidence of new activity or changes in ongoing eruptions since previous observations. The plumes provide real-time evidence of volcanic activity happening at the moment of observation, unlike surface features that might record activity from days or years past, visible only through accumulated deposits. Watching a plume erupt is watching Io's geology in action. The processes that reshape this world, made visible in a way that surface features alone cannot convey with equal immediacy. Each encounter reveals both familiar plumes, persisting as expected, and sometimes new ones appearing where none were seen before. The duration of individual plumes varies considerably, some persisting for years across multiple observation opportunities, while others appear briefly and then cease before the next spacecraft arrives. Pele's plume has been visible during most observations since Voyager, making it one of the most persistent features on this active world throughout the modern era of exploration. Other plumes have been observed only once, single events that happened to coincide with a spacecraft encounter, before falling quiet again and remaining dormant during subsequent observations. The mix of persistent and transient activity reflects the complex interior dynamics that drive Io's volcanism from below. The view of a plume from directly above is remarkably different from the side view that reveals the umbrella shape most clearly to observers looking at the scene. From above, the plume appears as a circular or irregular bright patch centered on the vent, the particles catching sunlight as they rise and fall through their ballistic paths together. The central vent may be visible as a darker spot within the brighter cloud, the source from which all the visible material originates before spreading outward. This perspective shows the extent of the plume without revealing its height, trading one dimension of understanding for another in the geometry of observation. The twilight zones where Io's surface meets the darkness of space provide opportunities to observe plumes against favorable backgrounds that enhance their visibility dramatically. When a plume rises above the sunlit surface into the zone where the sun has already set from the local perspective, it may catch sunlight while the terrain below sits in darkness. This creates striking silhouettes, the plume glowing against the black sky, the umbrella shape clearly defined by the contrast between illuminated particles and the shadow behind them. Some of the most beautiful images of Io ever captured show plumes in exactly this lighting geometry. The particles that make up the plumes eventually settle back to the surface, contributing to the ongoing geological burial that keeps Io's surface young and crater-free throughout the moon's history. The rate of material deposition from plume fallout can be estimated from the thickness of deposits and the frequency of eruptions, allowing scientists to calculate how quickly Io resurfaces itself through this aerial deposition process. Combined with surface lava flows that directly bury terrain beneath fresh, molten material, the plume deposits ensure that no part of Io's surface remains exposed for geologically significant periods of time. The surface is ephemeral, constantly being created and constantly being buried. A world with no permanent features in the geological sense. The colors of plumes reflect the composition of the material being ejected. Sulfur dioxide plumes appearing whitish, while sulfur-rich plumes take on yellows, and the larger silicate plumes may appear darker or more complex in coloration, depending on conditions. The colors are difficult to capture accurately because spacecraft cameras are calibrated for different purposes, and lighting conditions vary between observations. What remains clear is that the plumes contribute directly to the color palette of Io's surface, depositing material that will determine what color each region displays until the next eruption deposits a new layer above it. The plumes are painting the surface from above. The scale of these plumes becomes easier to grasp when considering what they would look like if they occurred on Earth, rising from familiar terrain to unfamiliar heights above. A plume the height of Pele's would extend from the ground past the edge of space and into the region where satellites orbit our planet safely above the atmosphere. Such an eruption would be visible from thousands of kilometers away, a fountain rising over the curve of the Earth, deposits falling across an area the size of a European country. Nothing like this has occurred on Earth in human history, and probably nothing quite like it has occurred since our planet's violent youth billions of years ago. The journey across Io's surface eventually brings every observer to Loki Patera, the single most powerful volcanic feature anywhere in the solar system, that produces more heat output than any other measured volcanic source. The name comes from the Norse trickster god, fitting for a feature that has puzzled scientists with its complex and sometimes unpredictable behavior since its discovery decades ago. Loki Patera is not a towering volcanic mountain like those found on Earth or Mars, but rather a vast depression filled with an active lava lake that covers more area than Lake Ontario on Earth. The dark surface of this lake contrasts sharply with the brighter surrounding terrain, creating a distinctive feature visible from great distances. The Patera spans roughly 200 kilometers across its irregular shape, making it one of the largest volcanic features on Io, despite being a depression rather than a peak or mountain. The term Patera refers to shallow volcanic craters, or calderas, features formed by collapse rather than construction, depressions where material has been removed from below, leaving the surface to settle. Loki Patera fits this definition perfectly, a vast sunken area where the underlying magma chamber has shaped the surface above through countless cycles of activity and collapse. The irregular outline suggests complex underlying structures, perhaps multiple connected chambers or varied geology beneath different portions of the visible feature. The lava lake within Loki Patera covers over 20,000 square kilometers of surface area, filled with molten material that is constantly being renewed from below through convection and resurfacing processes. The surface of this lake is normally dark, covered by a thin crust that forms when molten lava is exposed to the cold of space and solidifies into a skin above the still liquid material beneath. This crust is thin and unstable, constantly being broken and reformed as the convective motion of the lava below disrupts the surface pattern and exposes fresh, hot material. The lake never freezes solid because the supply of heat from below exceeds the rate at which the surface can radiate energy into space. An island rises from within the lava lake, a mass of solidified material that apparently has remained stable while the molten surface around it continues its endless cycling. This island stands as evidence that not everything within Loki Patera is equally molten, that some areas have solidified enough to persist, while others remain liquid and active. The island may represent older material that has accumulated enough thickness to resist remelting, or it may mark a region where the underlying heat source is locally weaker than elsewhere in the Patera. Whatever its origin, the island provides a reference point for observing changes in the surrounding lake over time. The brightening events at Loki Patera have drawn particular scientific attention. Periodic increases in heat output that suggest large-scale resurfacing events happening at roughly regular intervals. These events occur approximately every 500 Earth days on average. Though the timing varies and predictions based on past patterns do not always match observed behavior accurately. During a brightening event, the heat output from Loki increases dramatically as fresh hot lava is exposed across large portions of the lake's surface simultaneously. The cooler crust that normally covers the lake founders and sinks, replaced by molten material from below that glows brightly in infrared observations. The resurfacing process may proceed as a wave moving around the lava lake, starting at one location and propagating to others at a rate of about 1 kilometer per day until the entire lake has been renewed. This wave-like behavior suggests an organized process rather than random breakup of the surface crust, perhaps driven by convection patterns in the underlying magma that proceed in consistent directions. The wave begins when crust at one edge of the lake becomes dense enough to sink, exposing hot material that creates a local density instability that propagates to adjacent crust in sequence. The entire cycle takes roughly 500 days to complete, after which a new cycle begins as the newly formed crust ages and densifies. The temperatures at the surface of Loki Patera reach approximately 300 degrees Celsius in the cooler crusted areas, rising much higher where fresh lava is exposed directly. These temperatures are measured through infrared observations that detect the heat radiation emitted by the surface, a remote sensing technique that allows temperature mapping from orbital distances. The temperature distribution across the Patera shows hotspots where crust has recently broken, and cooler regions where the crust has had time to solidify and stabilize. The pattern changes constantly, a dynamic thermal map that reflects the ongoing activity within this vast volcanic feature. The view across the surface of the lava lake, from a hypothetical position at its edge, would be unlike anything available anywhere else in our solar system, or probably beyond. The dark crust, stretching toward the far horizon, would be broken by cracks and gaps where orange and yellow glow would indicate the molten material beneath showing through. Larger plates of crust might be visibly tilting as they destabilized and began to sink, fresh material welling up at the edges to replace them. The scene would be in constant slow motion, change visible over the course of hours or days. A lake that never stops moving even when it appears still. The heat output from Loki Patera alone exceeds the combined heat output of all volcanic activity on Earth, making this single feature more powerful than our entire planet's interior heat engine, expressed at the surface. This comparison highlights how extreme Io's volcanism truly is, concentrated in features that individually surpass everything our much larger and more massive world can produce, combined. The energy driving this activity comes not from radioactive decay as on Earth, but from tidal forces that we will explore later. An essentially infinite power source that cannot be exhausted through eruption. Loki Patera has been active for all of recorded observation and will continue for as long as Io orbits Jupiter. The edges of Loki Patera show complex geology where the lava lake meets the surrounding terrain, transition zones where flows have escaped the Patera boundary in past eruptions. These overflow events spread material across the adjacent surface. Dark flows that extend for tens of kilometers before cooling and solidifying to become part of the permanent landscape until the next eruption. The boundary is not static, but shifts over time as the Patera evolves through its endless cycles of activity. Some edge regions show multiple overlapping flows, a layered record of overflow events accumulated over centuries or millennia of activity. The comparison between Loki Patera and terrestrial lava lakes provides context that helps translate this alien feature into more familiar terms for understanding its nature. Earth has several active lava lakes, including Erta Ale in Ethiopia and the lake within Kilauea on Hawaii, where persistent molten surfaces exist for years or decades at a time. These terrestrial examples are tiny compared to Loki, covering areas measured in hundreds of meters rather than hundreds of kilometers, but the basic processes are similar at vastly different scales. The same physics governs the behavior of molten rock on both worlds. just expressed at extremes that Earth's lesser heat engine cannot approach. The trickster god's namesake feature continues to puzzle scientists with behavior that follows patterns imperfectly and occasionally surprises observers expecting repetition of previous cycles based on past observations. Some brightenings have occurred earlier or later than models predicted. Some have been more intense than expected. Some have shown different spatial patterns than previous events. This variability keeps Loki Patera interesting, despite decades of observation. Each new encounter with the Jupiter system offering opportunities to observe how the current cycle compares to past behavior. The trickster remains true to its name. The examination of Loki Patera could continue indefinitely, revealing new details at every scale and raising new questions about the processes that sustain such an extraordinary feature over geological time. For now, understanding that this single lava lake produces more heat than all of Earth's volcanoes combined conveys the essential character of what makes Io unique among all the worlds we know. The colors created by Io's volcanic activity relate directly to the chemistry of the materials involved, a palette worth exploring in its own right. The sulfur that coats everything on this world exists in many forms, each with its own color, and together they paint Io in hues found nowhere else. The colors of Io demand explanation, a palette so vivid and varied that early observers compared the moon to a pizza without fully appreciating the chemistry responsible for this remarkable appearance. The answer lies primarily in sulfur, an element with unusual properties that allow it to exist in many different molecular forms, depending on temperature and cooling history. Each form has a different color, and Io's surface experiences every relevant temperature range, creating natural conditions for the full spectrum of sulfur colors to appear. Understanding this chemistry transforms Io from an inexplicably colorful world into one whose appearance makes sense given what we know about its volcanic activity. Sulfur at its coldest, below about -100 degrees Celsius, appears white or very pale yellow, forming the frost deposits visible across much of Io's surface, away from active volcanic centers. This sulfur dioxide frost sublimates and reforms constantly as surface temperatures change through the day-night cycle and with distance from heat sources that warm local regions. The white patches on Io represent the coldest surfaces, areas farthest from volcanic activity, where temperatures remain low enough for this pale form to persist indefinitely. These frosty regions cover significant portions of the visible surface, providing the cool background against which warmer volcanic deposits stand out dramatically. As sulfur warms, it progresses through a sequence of color changes that reflect molecular rearrangements happening at the atomic level within the material being heated. Pale yellow gives way to brighter yellow, then to orange, then to red, and finally to dark red or brown at the highest temperatures sulfur can sustain before breaking down entirely. Each color represents a different arrangement of sulfur atoms, chains of varying length or rings of varying structure that absorb and reflect light differently. The temperature at which sulfur was last heated determines which molecular form it will take when it cools, locking in the color as a permanent record of its thermal history. The red rings around volcanoes like Pele indicate sulfur that was heated to very high temperatures during eruption, perhaps 600 degrees Celsius or higher, before being thrown into the cold of space. This extreme heating creates long-chain sulfur molecules that appear red and remain red even after cooling back to the frigid temperatures that prevail across most of Io's surface. The color is stable once formed, a permanent marker of past heat that persists indefinitely, unless new volcanic activity heats the material again and changes its molecular structure. These red deposits spread across enormous areas around the most powerful volcanic centers. Orange sulfur forms at intermediate temperatures, perhaps 200 to 400 degrees Celsius, and represents material that was hot, but not extremely so, during the deposition process. This color appears commonly across Io's surface, filling the zones between the intensely red regions nearest major volcanic vents and the yellow and white regions farther away. The orange creates a visual transition that reflects the thermal gradient, material deposited at progressively cooler temperatures as distance from the heat source increases. The gradual color change visible around volcanic features maps directly to the temperature gradient that existed during deposition. Yellow sulfur, the color most commonly associated with the element in everyday experience on Earth, forms at lower temperatures and represents material that was warm but not dramatically hot. This bright yellow color dominates much of Io's general background terrain, the default color of surfaces that have received some volcanic heating but not extreme temperatures during their most recent deposition. The yellow sulfur combines with the white sulfur dioxide frost in many regions, creating pale yellow surfaces that characterize the coldest portions of Io's visible globe. Even these relatively cold regions are still volcanic in origin, just heated less intensely. The black materials that interrupt the warm color palette are not sulfur at all, but fresh silicate lava. True molten rock, similar in composition to basaltic lavas on Earth, though heated to much higher temperatures. When this lava first reaches the surface, it retains its natural dark grey to black color, the color of solidified rock, before any coating of sulfur compounds has accumulated above it. Fresh flows appear as dark streaks and patches crossing the more colorful terrain, evidence of recent eruptions that have not yet been buried under the ever-present sulfur deposits. Over time, these dark flows will be covered, their original color replaced by whatever sulfur chemistry falls upon them from eruptions nearby. The color of any particular location on Io can change over time as new volcanic activity deposits fresh material over older deposits beneath, changing the visible surface layer repeatedly. A region that appears yellow today might be covered by orange deposits from a nearby eruption tomorrow, then by red deposits from a larger eruption next year. The colors are not permanent, but constantly evolving, a dynamic painting that never reaches a final state, because the processes creating it never stop their work. Old colors are buried beneath new colors in an endless cycle of deposition and coverage. Some of the color variations on Io may indicate different sulfur compounds rather than pure elemental sulfur in different molecular forms, adding chemical complexity to the temperature-based explanations that account for most of what we observe. Sulfur reacts with other elements present on Io, including sodium and chlorine that have been detected in the volcanic emissions and surrounding space environment. These compounds might contribute their own colors to the palette, creating hues that pure sulfur alone cannot produce through temperature variation. The complete chemistry of Io's surface remains an area of active research. The process of color change can be observed directly when conditions allow, with fresh volcanic deposits showing their initial colors before gradually being modified by subsequent activity and chemical change. Some spacecraft observations have captured areas during and shortly after eruption, showing the dark colors of fresh silicate lava before sulfur coating begins. Other observations have documented the same areas months or years later, showing how the original dark material has been covered by lighter deposits from continuing volcanic activity in the region. The surface is never static long enough for any color to become permanent. Viewing Io through different filters and at different wavelengths reveals additional color information invisible to eyes adapted for the narrow, visible range that defines human color perception naturally. Infrared observations show heat patterns rather than sulfur colors, mapping which areas are currently active versus which are cold and dormant temporarily. Ultraviolet observations reveal different aspects of the sulfur chemistry. Information about molecular states not visible in other wavelengths used for observation. The complete picture of Io's surface requires combining observations across multiple wavelengths into a comprehensive understanding. The overall impression of Io's color palette is of a world where chemistry and temperature combine to create art on a planetary scale, entirely without intention or design. No painter mixed these pigments, no artist chose this arrangement, yet the result achieves a visual impact that deliberately created art rarely matches in its strangeness. The pizza comparison fails because it suggests messiness, randomness, splatter, while Io's colors actually follow strict rules of chemistry and physics that create patterns meaningful to those who understand them. The colors tell the story of this world's activity to anyone who learns to read them. The chemistry that creates these colors depends ultimately on the energy that drives Io's volcanism. Heat that must come from somewhere to maintain activity on this scale indefinitely throughout geological time. Earth's volcanic activity is powered by radioactive decay within the interior, but this source is insufficient to explain Io's far more intense activity, given the moon's smaller size. The answer lies in the gravitational relationship between Io and Jupiter, a process called tidal heating that generates energy through flexing rather than through radioactive decay. Understanding this mechanism reveals why Io is so extraordinarily active among all the worlds we know. The question of what powers Io's extreme volcanism puzzled scientists before the answer became clear through careful analysis of the gravitational forces acting on this moon constantly. The energy cannot come from Io's own interior heat, because a body this size would have cooled long ago if only radioactive decay were contributing to the thermal budget. The answer is tidal heating, a process in which Jupiter's enormous gravity flexes Io's interior continuously, generating heat through friction that keeps the interior molten indefinitely. This mechanism makes Io unique, a world powered not by its own internal processes, but by its relationship with the giant planet it orbits nearby. Jupiter is massive, containing more mass than all the other planets in our solar system combined, about 318 times the mass of Earth altogether. This immense mass creates a gravitational pull that affects everything in the Jupiter system, including the 4 large Galilean moons that orbit in an orderly procession outward from the giant planet. Io orbits closest of the 4, at a distance of only about 422,000 kilometers from Jupiter's center. completing one full orbit in just 1.77 Earth days. This proximity means that Jupiter's gravitational influence on Io is strong enough to physically distort the Moon's shape throughout each orbit continuously. The tidal forces from Jupiter raise bulges in Io's solid rocky material, just as Earth's gravity raises tidal bulges in our oceans, and the Moon's gravity raises smaller bulges in Earth's rock. These tidal bulges on Io are approximately 100 meters high, the solid rock rising and falling by this amount as the Moon rotates and orbits through the varying gravitational field around Jupiter. If Io's orbit were perfectly circular, these bulges would remain stationary relative to Io's surface, pointing toward and away from Jupiter constantly without shifting. The constant bulge position would mean no internal friction, no heat generation, no volcanic activity powered by tidal forces at all. The crucial factor that makes everything work is the slight ellipticity of Io's orbit, a small deviation from circular that causes the distance to Jupiter to change continuously throughout each orbital period. When Io is closer to Jupiter, the gravitational pull is stronger, and the tidal bulges are higher and more pronounced than average. When Io is farther from Jupiter, the pull is weaker, and the bulges are smaller and less pronounced than average. This variation means the bulges must constantly grow and shrink, rise and fall, shift position slightly, as the changing gravitational pull reshapes Io's interior throughout every single orbit completed. The constant flexing of Io's interior generates heat through friction, the same way repeatedly bending a wire makes it warm through the mechanical energy being converted to thermal energy. This heat accumulates in Io's interior, raising the temperature high enough that much of the interior remains molten rock, magma that feeds the hundreds of volcanoes visible on the surface above. The energy input from tidal heating is estimated at roughly 100 trillion watts, an enormous power flow that exceeds Earth's total volcanic heat output by a factor of 30 to 40 times. This power has been flowing into Io for billions of years. The ellipticity of Io's orbit would normally disappear over time as tidal forces gradually circularize orbits through energy dissipation in the flexing body being heated. A circular orbit would mean no tidal heating, no internal melting, no volcanism. Io would become a cold, dead world like so many other moons in the solar system, frozen and dormant. Something prevents this circularization from happening. Something maintains the orbital eccentricity against the tendency to decay. And that something is the gravitational influence of the other large moons. Europa and Ganymede orbit farther from Jupiter, and their gravitational tugs on Io keep its orbit slightly elliptical, indefinitely. The mechanism by which the outer moons maintain Io's eccentricity will be explored more thoroughly when we examine the orbital resonance that links all three bodies together later in our journey. For now, the essential point is that the tidal heating cannot stop because the conditions that drive it are maintained by external forces that do not depend on Io's own state. Jupiter will continue to flex Io, and Io will continue to generate heat, and the volcanoes will continue to erupt for as long as this configuration of moons persists around the giant planet. The timescale for change is measured in billions of years. The interior structure of Io reflects the intense heating, with most of the moon's volume likely consisting of partially or fully molten rock, rather than the solid material that makes up most rocky body interiors. An outer crust of solidified rock floats atop this molten interior, thin enough that magma can easily break through to create the volcanic features we observe at the surface continuously. The crust may be only a few tens of kilometers thick. A fragile shell containing a sea of magma beneath that is constantly seeking routes to the surface. Every volcano on Io represents a location where this molten interior has found a path upward through weaknesses in the thin crust above it. The heat flowing outward from Io's interior must eventually escape into space, radiated away from the surface as infrared energy that spacecraft instruments can detect and measure from orbit. The total heat flow measured from Io exceeds what Earth produces despite Io being much smaller, a testament to the extraordinary efficiency of tidal heating as an energy source for geological activity. This heat loss is balanced by continuous heat input from the tidal flexing, creating a steady state where the interior remains molten and the volcanism continues unabated across geological time. The system has reached equilibrium, energy flowing in from gravity and flowing out as heat, with volcanic eruptions as the visible expression of this ongoing energy transfer. The temperatures involved in Io's volcanism support the tidal heating explanation, with some eruptions reaching temperatures that indicate silicate magma rather than lower temperature sulfur melts alone. Temperatures exceeding 1600 degrees Celsius have been measured at some volcanic vents comparable to the hottest lavas ever produced on ancient Earth during its earliest geological periods. These extreme temperatures require energy inputs that only tidal heating can plausibly provide for a body of Io's size, orbiting at this distance from the Sun. The warmth of the Sun itself contributes almost nothing to Io's internal heat budget at this distant location in the outer solar system. The visualization of tidal heating becomes clearer when imagining Io's interior over the course of a single orbit around Jupiter during those 1.77 Earth days. At the closest point in the orbit, called perigove, Jupiter's gravity pulls hardest, and Io's shape becomes most elongated toward and away from the giant planet, visibly. At the farthest point, called apogee, the pull is weaker, and Io's shape relaxes toward a more spherical form as the tidal bulges diminish in height. Between these extremes, the transition is continuous, the interior constantly adjusting its shape as the gravitational field changes with distance throughout the orbital period. This constant adjustment means that every piece of rock inside Io is being flexed, compressed, and released repeatedly, generating heat through the friction of material moving against itself internally. The heating is not uniform throughout the interior, but concentrated in regions where the flexing is most intense, likely in a partially molten layer between the core and the surface crust. This layer may be the source region for most of the magma that feeds the surface volcanoes, a global ocean of molten rock that sloshes and flows beneath the thin solid shell. The volcanoes are windows into this hidden ocean. The power of tidal heating becomes apparent when considering that it has maintained this state for approximately 4 billion years since the Jupiter system formed from the solar nebula. Earth's internal heat comes primarily from radioactive decay of elements like uranium, thorium, and potassium, distributed throughout the mantle and crust over time. This radioactive heating has been declining slowly as these elements decay, and Earth's interior is gradually cooling over geological timescales measured in billions of years of slow change. Io's tidal heating does not decay in the same way because the gravitational interactions that power it are not depleted by use. The comparison to Earth helps illustrate how unusual Io's situation truly is among the rocky bodies we have studied throughout the solar system. Earth is the most volcanically active planet in the inner solar system, with active volcanism along mid-ocean ridges, at subduction zones, and at hotspots like Hawaii. Yet Io produces perhaps 40 times more volcanic heat than Earth does, despite being only about 1/4 of Earth's diameter and possessing far less mass. The difference is entirely explained by the tidal heating mechanism, energy flowing in from outside rather than being generated internally through radioactive processes. The tidal heating on Io provides a model for understanding other moons in the solar system that show signs of internal activity, despite their small sizes and cold locations. Europa, the next moon out from Jupiter, experiences a milder version of the same process, which may maintain a liquid water ocean beneath its icy surface shell. Enceladus, a small moon of Saturn, shows active geysers that spray water ice into space, also likely powered by tidal heating from its orbital interactions with other moons. Io was the first place where scientists recognized this heating mechanism operating at full intensity, changing our understanding of what small moons can do. The surface we have been exploring throughout this journey exists because of the energy flowing upward from the tidally heated interior below, continuously and reliably. Every plume, every lava lake, every fresh flow of molten rock, every deposit of sulfur in all its colors represents the surface expression of gravitational energy being converted to heat deep within Io's flexing interior. The giant planet in the sky is not merely a backdrop, but the engine driving everything we have observed on this remarkable volcanic moon. Jupiter's gravity reaches down into Io and squeezes, and volcanoes are the result of that squeeze, continuing forever. The understanding of tidal heating allows us to see Io not as a strange exception, but as an example of a general process that operates wherever the conditions are right throughout the universe. Any moon orbiting close to a massive planet with a slightly eccentric orbit will experience some degree of tidal heating from these inevitable gravitational interactions. Io simply shows this process at its most extreme, the most dramatic example we have found of what gravity can do to a world caught in its grip. The flexing continues as you watch, invisible but relentless. The volcanic activity that reshapes Io continuously has an observable consequence visible in the very appearance of the surface, when examined for features that should be present but are not. Impact craters are missing from Io's surface entirely, despite the fact that every other solid body in the solar system displays some record of cosmic bombardment accumulated over time. This absence tells us something remarkable about how quickly the surface is being replaced, renewed faster than craters can accumulate through the random arrival of asteroids and comets over millions of years. The surface of Io is young in a way that no other surface we have examined anywhere in the solar system can match. The logic of crater counting as a dating method is straightforward and has been applied successfully throughout the solar system for decades of planetary science research. Older surfaces accumulate more craters because they have been exposed to impacts for longer periods, while younger surfaces have fewer craters because less time has passed since their formation. The moon's heavily cratered highlands are ancient, perhaps 4 billion years old, while the darker mare regions are younger at around 3 billion years, based on their lower crater densities. Every solid surface in the solar system tells its age through the craters it has accumulated, except for Io. Io orbits within the Jupiter system where impacts should occur, sharing space with countless small objects that occasionally strike all 4 Galilean moons over time. Callisto, the outermost of the 4 large moons, is one of the most heavily cratered bodies known, its surface recording billions of years of bombardment, clearly visible. Ganymede shows regions of heavy cratering, alongside younger terrain with fewer impacts, indicating a geological history with active and quiet periods alternating. Europa has relatively few craters, suggesting an active surface that renews itself, though not as actively as Io, which has none at all. The complete absence of recognizable impact craters on Io means the surface renewal rate exceeds the rate at which craters form, erasing them faster than they can accumulate permanently. Estimates suggest that the entire surface of Io may be replaced on timescales ranging from thousands to hundreds of thousands of years, extraordinarily fast in geological terms compared to any process on Earth or elsewhere. One common estimate suggests roughly 1 centimeter of new material is deposited across the entire surface each year through volcanic processes operating continuously everywhere. Over 1 million years, this would bury any crater under 10 kilometers of fresh volcanic deposits. The resurfacing happens through multiple mechanisms working simultaneously across the entire moon, at all times throughout its endless volcanic activity period. Lava flows extend across the surface, burying everything in their paths as they spread from volcanic vents across the surrounding terrain for hundreds of kilometers. Plume deposits rain down from above, sulfur and silicate particles falling back to the surface after being ejected high into the sky by explosive eruptions. Volcanic mountains grow and collapse, calderas form and fill, the entire landscape constantly shifting as new features form and old features disappear beneath fresh material. A lava flow crossing older terrain erases whatever existed beneath it, covering previous flows, previous deposits, any craters that might have formed in the interval since the last eruption at that particular location. The flow spreads across the surface, cooling from the top down, forming a fresh, dark surface that will eventually be coated in sulfur deposits as the chemistry of this world repaints everything. The previous surface is gone, buried, incorporated into the growing stack of volcanic materials that accumulates over time at rates unmatched anywhere else. The geological record is being continuously erased, even as new records are written above. The plume deposits contribute equally to the resurfacing, material ejected hundreds of kilometers into the sky, eventually falling back to coat the surface within the deposit rings that surround each active volcanic center. These deposits can cover areas larger than some countries on Earth. Fresh material settling over everything within range of the eruption's spreading umbrella pattern. Over time, repeated eruptions build up thick sequences of plume deposits that bury whatever features existed before the volcanic activity reached that particular region. The sulfur compounds that color Io's surface are partly these accumulated plume fallback deposits. The volcanic mountains of Io also participate in the resurfacing through their growth, collapse, and reformation over timescales that might be quite short by geological standards of comparison. Some mountains on Io rise over 15 kilometers above the surrounding terrain, higher than any mountain on Earth relative to surrounding plains. These mountains may form through compression as volcanic materials accumulate and push against each other, or through tilting of crustal blocks as the surface adjusts to underlying volcanic activity. Mountains can collapse as well, landslides and structural failures, adding debris to the surrounding terrain. The constant renewal means that Io keeps no permanent record of its past, in the way that other bodies do through their accumulated surfaces over billions of years. We cannot look at Io's surface and read its history the way we can read the Moon's history from its cratered highlands and younger mare basins clearly. The oldest surfaces on Io may be only thousands of years old, younger than human civilization on Earth, constantly being replaced by fresh volcanic material from below. The past is buried, overwritten, erased by the present volcanic activity that never pauses long enough to leave lasting records. The rate of volcanic output required to maintain this resurfacing is staggering when calculated in terms of material being erupted per unit time across the entire Moon. Io may produce roughly 100 times more lava per year than Earth does. Despite being so much smaller, all of this material coming from the tidally heated interior below. This output would be enough to bury the entire surface of Io in fresh volcanic materials to a depth of several centimeters each year, if spread evenly. The actual distribution is not even, concentrated at active volcanic centers, but the global average tells the story of total renewal. The title's claim that Io turns itself inside out becomes literally accurate when considering what this resurfacing means over longer timescales of geological activity. Material from the deep interior reaches the surface through volcanic eruptions, is deposited, then is eventually buried by newer deposits, and may be recycled back into the interior through processes we do not fully understand yet. The entire volume of Io's outer layers may have cycled through the surface multiple times over the 4 billion-year history of volcanic activity on this Moon. Inside becomes outside, outside becomes inside, the Moon continuously recycling itself. Standing on the surface, you would not see this renewal happening in any dramatic fashion, despite the incredible rate at which it occurs globally. The changes happen at the pace of geological processes, detectable over years and decades, but not visible in any single moment of observation directly. Yet the evidence is there in the absence of craters, in the freshness of the terrain, in the colors that indicate recent volcanic activity almost everywhere you look across this restless surface. The ground beneath you is young, perhaps younger than any natural surface you have ever walked upon on Earth. The youth of Io's surface contrasts dramatically with the ancient surfaces visible on the other Galilean moons, orbiting nearby in the same Jupiter system together. Callisto's surface may be 4 billion years old, unchanged since the early solar system, except for the continued accumulation of impact craters over time. Ganymede preserves regions nearly as old, alongside younger terrain that tells of past geological activity, now long ceased in those specific regions. Europa's surface may be only tens of millions of years old on average, renewed by processes beneath its icy shell at rates much slower than Io's. Only Io shows the present tense of geological activity. The comparison helps place Io in context, a moon that cannot preserve its past, because its presence is too active, too consuming, too comprehensive in its renewal of everything across the entire surface continuously. The volcanoes we have visited, the plumes we have watched, the lava lakes we have observed are all participating in this process of erasure and renewal simultaneously. What we see today will be gone tomorrow in geological terms, buried beneath the next eruption, the next flow, the next deposit falling from the latest plume. Io lives entirely in the present. The surfaces of other worlds serve as history books, recording events from millions and billions of years ago in the craters and formations they preserve across their ancient terrains. Io serves a different function, demonstrating what active geology looks like when it operates at maximum intensity, without pause or interruptional timescales. The absence of history is itself the most profound historical statement this moon can make about its nature and its activity levels, sustained over billions of years. The blank page tells us the pen never stops writing. As we continue our exploration, we turn from the solid surface to the thin envelope of atmosphere that exists above it under certain conditions only. This atmosphere behaves in ways unlike any other atmosphere in the solar system, collapsing and reforming with each orbit around Jupiter as conditions change dramatically between sunlight and shadow. The thin envelope of gas surrounding Io cannot be called an atmosphere in the way we normally use that word for the thick, persistent layers of gas that surround Earth or Venus or even Mars. Io's atmosphere is extraordinarily thin, with surface pressure less than 1/1,000,000th of Earth's sea level atmospheric pressure, barely distinguishable from the vacuum of space by most measures. This wispy covering of sulfur dioxide gas comes and goes depending on conditions, building up when the surface is heated by sunlight and collapsing when darkness and cold return. The behavior is unique in the solar system. The primary component of Io's atmosphere is sulfur dioxide, the same gas released constantly by volcanic eruptions across the surface and present as frost in many regions between active volcanic centers. This gas sublimates directly from the frost when sunlight warms the surface, rising into the thin atmosphere above without passing through a liquid phase, as water does on Earth. The volcanic vents also contribute sulfur dioxide directly to the atmosphere, pumping fresh gas upward through eruptions that add to what sublimation provides during daylight hours. Both sources contribute, though scientists continue to study the relative importance of each mechanism. The atmospheric pressure varies dramatically, depending on location and conditions present at any given time across Io's surface during an orbit. Near active volcanic vents, the atmosphere is denser, supported by continuous outgassing from the volcanic activity happening below the thin atmospheric layer. Over cold regions far from volcanic activity, the atmosphere is thinner because less sublimation occurs from the frozen surface materials present there. The patchiness of Io's atmosphere reflects the patchiness of its volcanic activity and surface temperatures across the varied terrain. The most remarkable behavior occurs when Io passes into Jupiter's shadow, an event that happens during nearly every orbit and plunges the moon into darkness for approximately 2 hours each time. When sunlight disappears, the surface temperature drops rapidly because there is almost no atmosphere to retain heat through any greenhouse effect whatsoever. As the temperature falls, the sulfur dioxide gas in the atmosphere begins to condense, freezing out of the thin air and falling as frost onto the surface below. The atmosphere partially collapses during each eclipse. The collapse happens within minutes of entering Jupiter's shadow, the atmospheric density decreasing by a factor of roughly 5 as gas freezes onto the suddenly cold surface below. This is not a gradual seasonal change like the freezing of carbon dioxide at Mars's polar caps during winter months, lasting many Earth weeks. This is a rapid collapse and reformation cycle that repeats with every single orbit, every 1.77 Earth days, throughout the entire history of Io's existence. The atmosphere falls and rises twice during every orbital period completed. When Io emerges from Jupiter's shadow back into sunlight, the frozen sulfur dioxide begins to sublimate again, rebuilding the atmosphere from the surface upward as warming spreads across the terrain. The process takes perhaps 10 to 20 minutes to restore the atmosphere to its pre-eclipse density, the gas rising from the warming frost and volcanic vents resuming their contribution to the atmospheric pressure. This cycle has repeated billions of times over Io's history, the sky collapsing and reforming with each passage through shadow, like breathing in and out. No other world does this. The visualization of atmospheric collapse requires imagining the thin haze above an active volcanic region, fading as shadow sweeps across the surface from the approaching darkness of Jupiter's bulk blocking the sunlight. The volcanic plumes might continue rising because they are powered by internal heat rather than solar warming, but the background atmosphere thins noticeably around them as sublimation stops and condensation begins. Frost forms on surfaces that were bare rock moments before, the sulfur dioxide literally falling out of the sky as temperatures plunge through the freezing point of this particular gas. The ground whitens slightly with fresh frost deposition. The return of sunlight reverses everything. The frost beginning to sublimate immediately as photons warm the surface and temperatures climb above the threshold where sulfur dioxide must exist as gas rather than solid. The haze returns, thickening around volcanic vents where the combination of sublimation and direct volcanic emission restores the atmosphere most quickly after each eclipse. The timing is predictable because the orbital period is fixed, every eclipse lasting approximately the same duration as every other eclipse throughout the endless repetition of Io's orbit around Jupiter. The sky breathes in and out on schedule. The thinness of even the fully developed atmosphere means that Io cannot be said to have weather in any meaningful sense compared to worlds with substantial atmospheric circulation patterns. There is no wind capable of transporting significant amounts of material laterally across the surface through atmospheric motion as happens on Earth or Mars constantly. The volcanic plumes rise and fall under their own momentum, and Io's weak gravity, not affected by atmospheric drag or deflection by wind currents that do not exist at these pressure levels. The atmosphere is present but passive. The lack of atmospheric protection means that Io's surface is exposed directly to space in most practical senses, despite the technical presence of some gas above the ground surface. Radiation from Jupiter's magnetosphere reaches the surface unimpeded by atmospheric absorption, or scattering that might reduce its intensity significantly. Micrometeorites strike the surface without burning up in atmospheric entry, as they would on Earth or even Mars, though these impacts contribute little to the surface compared to the overwhelming volcanic resurfacing happening continuously. The atmosphere is there, but it protects nothing. The The sulfur dioxide atmosphere extends only a few hundred kilometers above the surface, at most, far thinner than the volcanic plumes that can reach 500 kilometers or more in height during major eruptions. In fact, the plumes rise through the atmosphere and above it, escaping into what is essentially space before their material falls back to the surface, following ballistic trajectories unaffected by any atmospheric drag. The plumes are not geysers in the traditional sense of steam rising through air, but are more like fountains spraying into vacuum directly. The atmosphere is beneath them, rather than around them. The detection of Io's atmosphere required careful observation because the gas is so thin that it produces no visible effects from most observing distances and angles used by spacecraft. Ultraviolet observations revealed the presence of sulfur dioxide through its absorption of specific wavelengths of light passing through the atmospheric layer toward detectors. Later observations confirmed the atmospheric collapse during eclipses by noting changes in this ultraviolet signature as Io entered and exited Jupiter's shadow repeatedly. The atmosphere is real but subtle, requiring sensitive instruments to detect its presence. Some regions of Io may have locally denser atmospheric patches where volcanic activity is particularly intense, and gas emission rates exceed what the surrounding environment can absorb through condensation or loss to space. These local enhancements create a complex atmospheric structure that varies across the surface according to the distribution of active volcanic centers below. The atmosphere is not a uniform shell, but a patchy, variable envelope that reflects the equally patchy and variable volcanic activity, producing most of the gas involved. Volcanic regions are atmospheric regions on this world. The loss of atmospheric material to space is ongoing, stripped away by Jupiter's intense magnetosphere and the radiation environment that bombards Io continuously throughout every orbit. This loss would deplete the atmosphere entirely over relatively short timescales if volcanic emissions did not replenish what is lost to space at comparable rates. The atmosphere exists in dynamic equilibrium, gas being added by volcanism and sublimation, while simultaneously being lost to Jupiter's magnetosphere through interactions we will explore shortly. Io bleeds material into space. The experience of standing on Io's surface would not involve any awareness of the atmosphere because it is far too thin to scatter light or create any sky color beyond the black of space itself directly. Overhead, Jupiter would hang in a black sky regardless of whether the sun was up or down. No blue or pink or any other atmospheric tint coloring the view in any direction around the horizon. The stars would be visible even during daylight hours because no atmospheric scattering brightens the sky around the sun's position. This is a world with sky, but without atmosphere in any visual sense. The collapsing atmosphere represents one more way that Io differs from every other world we have explored. One more feature that makes this moon extraordinary among all the bodies in the solar system visited by spacecraft. The ground reshapes itself continuously. The interior remains molten through external heating, and even the sky comes and goes with each orbit completed. Nothing about Io is stable in the ways we expect worlds to be stable over geological timescales. Everything changes constantly. The radiation environment surrounding Io makes this moon one of the most hostile places in the entire solar system for anything sensitive to energetic particles, including spacecraft electronics and any hypothetical biological organisms. Jupiter possesses the most powerful planetary magnetic field known, trapping charged particles in radiation belts that dwarf Earth's Van Allen belts by every measure of intensity and extent. Io orbits deep within these radiation belts, bathed in energetic particles that would deliver lethal doses to unprotected humans within minutes of exposure. The environment is harsh beyond imagination. The source of this radiation is ultimately the Sun, which continuously emits charged particles in the solar wind flowing outward through the entire solar system at speeds of hundreds of kilometers per second. Jupiter's magnetic field captures some of these particles, redirecting them along magnetic field lines and trapping them in toroidal regions around the planet, where they accumulate over time to dangerous concentrations. Additional particles come from Io itself, volcanic emissions that are ionized and incorporated into the radiation environment through complex interactions with Jupiter's magnetic field. Io contributes to its own hostile environment. The intensity of radiation at Io's orbital distance from Jupiter reaches approximately 3,600 rem per day, a number that becomes meaningful when compared to radiation levels familiar from Earth environments and safety standards used on our planet. Earth's natural background radiation delivers roughly 0.3 rem per year from cosmic rays and terrestrial radioactive materials, combined over 12 months of continuous exposure. A single day on Io's surface would deliver more than 10,000 times the annual radiation dose received naturally on Earth's surface by all inhabitants. The numbers are almost incomprehensible. The lethal dose for humans is generally considered to be around 400 to 500 rem, delivered over a short period, causing acute radiation syndrome that proves fatal within days or weeks, without extraordinary medical intervention. Io's surface would deliver this lethal dose in approximately 2 to 3 hours of unshielded exposure to the radiation environment present continuously at all times. No biological organism from Earth could survive on Io's surface for meaningful periods. And even radiation-hardened spacecraft electronics suffer degradation from the intense particle bombardment during close approaches. This is a world hostile to technology. The interaction between Io and Jupiter's magnetic field produces remarkable electromagnetic phenomena that connect the Moon to the giant planet through invisible structures of flowing current and energy. As Io moves through Jupiter's magnetic field, it generates electrical currents through a process similar to how a generator produces electricity by moving conductors through magnetic field lines on Earth. These currents flow along the magnetic field lines, connecting Io to Jupiter's upper atmosphere, creating a structure called the Io flux tube that carries energy between the two bodies. The power involved is substantial. The Io flux tube carries approximately 2 trillion watts of electrical power, more than all the power plants on Earth generate combined at any given moment of continuous operation. This energy flows from Io to Jupiter along the magnetic connection, eventually being deposited in Jupiter's upper atmosphere, where the field lines terminate in both the northern and southern hemispheres. Where the flux tube meets Jupiter's atmosphere, it creates permanent auroral spots that glow with the energy being delivered from the volcanic moon across hundreds of thousands of kilometers. These spots are visible in ultraviolet images. The visualization of this system requires imagining invisible magnetic field lines extending from Io to Jupiter like the strings of an enormous instrument being plucked by the moon's motion through the field. Current flows along these lines, carried by charged particles streaming in both directions between the moon and the planet through the magnetic connection, continuously. The auroral spots on Jupiter mark the footprints of this connection, one in each hemisphere, glowing ovals that track Io's position as the moon orbits, and the connection point moves across Jupiter's upper atmospheric layers. The glowing spots have been photographed. Material from Io escapes continuously into the surrounding space, stripped away by the intense radiation and electromagnetic interactions that characterize this moon's relationship with Jupiter's magnetic field environment. Roughly 1 ton of material per second leaves Io and enters the magnetosphere, primarily sulfur and oxygen atoms that have been ionized by the radiation environment and captured by magnetic field lines, carrying them away. This material does not simply disperse randomly, but accumulates in a specific structure, orbiting Jupiter along Io's orbital path. A visible ring of plasma forms. The Io plasma torus is a donut-shaped region of ionized gas that surrounds Jupiter at approximately Io's orbital distance, fed continuously by material escaping from the volcanic moon's surface and thin atmosphere into space. This torus glows in ultraviolet light from the ionized sulfur and oxygen it contains, creating a visible structure that traces Io's orbit around the giant planet completely. The torus contains perhaps 5 million tons of material at any given time, continuously supplied by Io and continuously lost to other regions of Jupiter's magnetosphere through complex plasma physics. Io is leaking. The plasma torus influences Io's environment, even as Io creates and maintains the torus through ongoing volcanic emissions of the material involved in this system. Radiation from the torus adds to the already intense radiation environment at Io's orbital distance, compounding the challenges for any spacecraft attempting to operate near this volcanic moon. The torus also interacts with the other Galilean moons, particularly Europa, which orbits through the outer edges of this plasma structure during its own orbital path around Jupiter. Everything in the inner Jupiter system is connected. The practical implications of this radiation environment have shaped exploration strategies for the Jupiter system throughout the history of space exploration missions to this distant region. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, made only limited close approaches to Io, because each approach exposed the spacecraft to radiation that degraded its systems progressively. Even with radiation hardening, the spacecraft accumulated damage with each pass through the intense environment near Io's orbit, limiting the observations possible during its mission lifetime. Future missions face similar constraints. The proposed Io Volcano Observer mission would study Io from closer distances than any previous spacecraft has achieved for extended periods near this radiation-hostile environment. This mission would require advanced radiation shielding and would still need to limit its time in the most intense regions to preserve spacecraft functionality throughout a useful mission lifetime. The radiation is a feature of the environment that cannot be eliminated, only managed through mission design choices that balance scientific return against system degradation rates. Io demands respect. Standing on Io's surface would be impossible for humans, not only because of the cold and the vacuum, but also because of the radiation that penetrates everything and deposits energy in any material it encounters continuously. The volcanoes and plumes we have explored exist in an environment that would be immediately lethal. A beautiful but deadly landscape, visible only through robotic eyes, protected by careful engineering against the harsh particle environment. The visual splendor of Io comes with a price that keeps it forever beyond human experience through direct presence. We can only watch from distance. The flux tube and plasma torus represent Io's influence extending far beyond its small physical size into the broader Jupiter system through electromagnetic connections invisible to ordinary observation. This tiny moon, smaller than Earth's moon, pumps material and energy into the Jupiter system continuously, shaping the plasma environment for millions of kilometers around the giant planet. The volcanic activity we have explored on the surface has consequences that reach across interplanetary distances, connecting Io to Jupiter through bonds stronger than gravity alone. The moon shapes its environment. The question of why Io remains volcanically active after billions of years has an answer that involves not just Jupiter, but the other large moons orbiting in careful gravitational relationship nearby. The orbital resonance linking Io, Europa, and Ganymede maintains the conditions necessary for tidal heating to continue indefinitely, without the orbit circularizing and the heating stopping. This gravitational dance has persisted since the Jupiter system formed and will continue for billions of years more, keeping Io's interior molten and its volcanoes active through mechanisms beyond the moon's own control. The answer lies in mathematics. The orbital periods of the three moons follow a precise numerical relationship that creates the resonance maintaining Io's volcanic activity continuously. For every single orbit Io completes around Jupiter, Europa completes exactly 1/2 of an orbit around the same planet. For every orbit Europa completes, Ganymede completes exactly 1/2 of an orbit at its greater distance from Jupiter. This creates a 4:2:1 ratio. Io orbits 4 times for every one Ganymede orbit, with Europa at the midpoint completing 2 orbits in the same period. The timing is exact. This relationship is called a Laplace resonance, named after the French mathematician Pierre-Simon Laplace, who analyzed the gravitational dynamics of the Jupiter system in the early 19th century using mathematical techniques. The resonance is not coincidental, but self-maintaining. The gravitational interactions between the moons acting to preserve the relationship against perturbations that might otherwise disrupt it over time. If one moon drifted slightly from its resonant position, the gravitational pulls from the other moons would act to restore it to the correct orbital period. The system corrects itself. The importance of this resonance for Io's volcanism lies in how it maintains the slight ellipticity of Io's orbit against the tendency for tidal dissipation to circularize that orbit over time through energy loss. The gravitational tugs from Europa and Ganymede, delivered at regular intervals when the moons align in specific configurations, prevent Io from settling into a circular orbit that would end the tidal heating mechanism. Each alignment delivers a small perturbation that keeps the orbit slightly elliptical, maintaining the conditions necessary for continuous tidal flexing and heating. The outer moons keep Io active. The alignments occur because the resonance ensures the moons return to the same relative positions repeatedly throughout their endless orbits around Jupiter together. When Io passes between Europa and Jupiter, the gravitational pull from Europa adds to or subtracts from the gravitational pull from Jupiter in predictable ways that affect Io's orbital shape incrementally. These effects accumulate over many orbits to maintain the eccentricity at roughly constant values, despite the energy being dissipated as heat inside Io continuously through tidal flexing. The heating continues because the eccentricity continues because the resonance continues. The visualization of this orbital dance requires seeing all three moons in motion simultaneously, each traveling its own orbital track at its own speed, while maintaining the mathematical relationship that links their periods together precisely. Io races around the innermost track, completing an orbit every 1.77 days and passing the slower outer moons repeatedly throughout its journey. Europa moves more slowly, taking 3.55 days per orbit, and Ganymede moves slower still at 7.15 days per orbit around Jupiter. The timing locks together. From above Jupiter's north pole, the dance appears as three dots moving in concentric circles, the inner dot racing, the middle dot proceeding at moderate pace, and the outer dot moving sedately, while all three maintain their harmonic relationship perfectly. Every time Io completes 4 orbits, the pattern repeats, the 3 moons returning to the same relative positions they held before, ready to begin the cycle again immediately. This pattern has repeated billions of times since the Jupiter system formed, and will continue until the Sun itself runs out of fuel and dies. The dance is eternal. The energy powering Io's volcanism ultimately comes from the orbital energy of the Moon system, extracted through tidal interactions and converted to heat that drives the volcanoes we have explored throughout this journey. Over billions of years, this energy extraction causes the orbits to evolve slowly, the moons spiraling slightly inward or outward as energy is shuffled between them through their gravitational interactions. The evolution is slow enough that the system remains stable over the lifetime of the solar system, but changes accumulate over timescales even longer than the Sun's eventual death. The dance evolves slowly. Europa experiences its own tidal heating from the same resonance mechanism, though at lower intensity than Io, because Europa orbits farther from Jupiter, where the tidal forces are weaker. This milder heating may maintain a liquid water ocean beneath Europa's icy surface, keeping the ice shell thin enough that cracks and ridges form as the shell flexes during each orbit completed. Ganymede, farthest of the 3 resonant moons, experiences the least tidal heating, but may still have some internal activity as a result of its participation in the orbital dance. The resonance affects all 3 moons. The existence of this resonance was known long before its implications for volcanic activity were understood by scientists studying the Jupiter system from Earth-based observations. Astronomers observed the moons moving in their orbits and calculated the resonant relationship from the timing of eclipses and transits visible across the enormous distance separating Earth from Jupiter continuously. Only when tidal heating was proposed as an energy source for Io's volcanism did the significance of the resonance for maintaining this heating become clear to researchers. The mathematics preceded the geology. The stability of the resonance over billions of years ensures that Io will remain volcanically active for as long as the Jupiter system exists in approximately its current configuration around the Sun. The volcanoes will continue erupting, the plumes will continue rising, the lava lakes will continue overturning, The surface will continue renewing itself through processes that began shortly after the solar system formed and show no signs of stopping. The heat flows in from Jupiter's gravity through the orbital dynamics that the resonance maintains, an external energy source that cannot be depleted by being used. The furnace has unlimited fuel. The other Galilean moon, Callisto, orbits beyond the resonance and experiences no significant tidal heating as a result of its isolation from the orbital dance linking the inner three moons together. Callisto's surface is ancient and heavily cratered, cold and geologically dead for billions of years, showing what Io might look like if the resonance did not exist to maintain its activity continuously. The contrast between Callisto's ancient surface and Io's constantly renewed terrain demonstrates the power of the resonance to maintain geological activity against the tendency for small bodies to cool and die over time. Position matters. The Jupiter system serves as a laboratory for understanding tidal heating and orbital resonances that may operate elsewhere in the universe, around other giant planets, orbiting other stars in distant solar systems. Exoplanet researchers look for similar configurations in the planetary systems they discover, wondering whether moons around giant exoplanets might experience the same heating that makes Io so volcanically active in our own solar system. The principles we have learned from studying Io apply universally wherever gravity and orbits interact to generate heat in small bodies far from their stars. Io teaches universal lessons. The experience of night on Io differs from night on any other world we have explored because Jupiter dominates the sky with a presence that prevents true darkness from ever arriving. When the sun sets below Io's horizon, the giant planet remains visible, reflecting enough sunlight to illuminate the volcanic landscape below, with a brightness far exceeding any moonlight Earth has ever known. The darkness is not dark, the night is not quiet, and the volcanoes continue their activity regardless of whether the sun has risen or set above the tortured surface. Night on Io is a different kind of experience. Jupiter appears enormous from Io's surface, spanning approximately 38 degrees of sky, nearly 40 times wider than the full moon appears from Earth's surface by comparison. You could not cover Jupiter with your hand held at arm's length, because the planet would extend beyond your spread fingers in all directions significantly. The banded clouds are clearly visible, the zones and belts of different colors wrapped around the giant planet in horizontal stripes driven by wind patterns and atmospheric chemistry we cannot see from this distance, but know exist from closer observation. The Great Red Spot might be visible if it happens to face Io during your observation period. The illumination from Jupiter during Io's night is estimated at roughly 100 times brighter than the full moon illuminates Earth's night side. Bright enough to read by if books existed on this hostile surface. Bright enough to see surface features clearly without any artificial lighting required. The volcanic landscape appears in muted colors under this reflected light. The sulfur yellows and reds, visible but softer than they appear in direct sunlight during the day. Shadows exist, but are gentler. Multiple light sources from Jupiter's extended disk, creating overlapping illumination patterns across the terrain. Jupiter light paints everything. The surface still glows in places where volcanic activity continues, regardless of solar illumination. Lava lakes and active vents producing their own light that stands out against the Jupiter-lit landscape around them visibly. These glowing points mark the locations of ongoing eruptions, hotspots that never cool because the tidal heating driving them operates continuously without reference to day or night cycles in the Jupiter system. From a distance, the night side of Io might appear spotted with volcanic glows, a world whose internal activity creates light where no external light sources operate directly. The volcanoes shine in darkness. The other Galilean moons are visible in Io's sky as well. Bright points of light moving against the fixed background of stars according to their orbital periods and current positions relative to Io's location. Europa appears roughly twice the diameter of Earth's moon from Io's perspective. Close enough and large enough to show a visible disk under good observation conditions, rather than appearing as a mere point of light like most celestial objects. Ganymede and Callisto appear smaller but still brighter than any star, their positions shifting noticeably over hours as all 4 moons proceed through their orbits. Fellow travelers share the sky. The stars themselves appear unusually steady from Io's surface because there is essentially no atmosphere to create the twinkling effect that makes stars shimmer when viewed through Earth's thick air. Without atmospheric turbulence to distort incoming starlight, each star appears as a fixed point of unwavering brightness against the black sky surrounding Jupiter's enormous glowing presence. The Milky Way stretches across the regions of sky not dominated by Jupiter's disk. The galaxy's structure, visible with clarity matched only by the best observing conditions available on Earth. Space appears very close. Jupiter rotates quickly, completing 1 rotation in just under 10 hours, meaning that surface features visible on the giant planet change noticeably over the course of a single Io night, lasting approximately 20 hours from sunset to sunrise. The Great Red Spot might rise into view, cross the visible face, and set again during a single night on Io if timing aligns correctly with the observation period chosen. The cloud patterns shift and evolve as atmospheric dynamics continue their endless circulation around the giant planet, a slow-motion animation playing out on the enormous screen that dominates Io's night sky constantly. Jupiter is active too. The psychological experience of this night would feel profoundly alien to anyone conditioned by Earth's familiar cycle of dark nights and bright days, alternating predictably. There is no darkness here, no escape from the giant planet's presence, no moment when the sky empties of illumination and allows stars to dominate the entire visible hemisphere around you. Jupiter is always there when visible, an enormous eye watching everything that happens on its small volcanic moon continuously without pause. The light never fully fades to what Earth creatures would call night. The temperature drops significantly after sunset, despite Jupiter's illumination providing substantial light, because the light from Jupiter carries very little heat compared to direct solar illumination during Io's day. The surface cools rapidly in the thin atmosphere that provides no insulation against heat loss to space, temperatures dropping by perhaps 50 degrees or more during the night hours away from active volcanic regions. Near the volcanoes, temperatures remain elevated regardless of the day-night cycle because internal heat dominates over solar heating in those locations anyway. Cold spreads across passive surfaces. A volcanic eruption viewed at night would appear particularly dramatic. The glowing lava and rising plume standing out against the darker background of Jupiter-lit terrain, rather than competing with direct sunlight for visual attention. The plume might catch Jupiter light high above the surface, appearing as a ghostly column rising from the glowing source below into the darkness above, where even Jupiter's illumination fades to black. The eruption would be silent in the vacuum, no sound accompanying the visual spectacle of molten rock founaining hundreds of kilometers into the sky. From vents below, beauty and violence combine silently. The night eventually ends as Io's rotation brings the sun back above the horizon. The transition from Jupiter light to sunlight, happening gradually as the sun climbs into the sky to join the giant planet that never sets from many locations on this tidally influenced moon. The colors intensify as direct illumination returns, the sulfur deposits appearing brighter and more saturated than they did under Jupiter's reflected glow alone during the night. The temperature begins to climb again, frost potentially sublimating from surfaces that accumulated it during the coldest hours before dawn arrived. Day returns to Io. The cycle repeats continuously, day and night alternating every 10 hours or so, depending on exact location and orbital geometry. Jupiter present during both phases to dominate the sky whenever it faces the observer's position on Io's surface. This is a world where the presence of the giant planet shapes every aspect of existence. From the volcanic activity driven by tidal heating, to the illumination of the night sky, to the radiation environment that bathes everything continuously. Io exists in Jupiter's shadow, figuratively, even when outside it, literally. The relationship defines everything. The journey across Io's volcanic surface draws towards its conclusion as we step back to see this moon as a complete world existing within the Jupiter system that defines its nature and activity levels continuously. What we have explored is the most volcanically active body in the known solar system, a world that reshapes itself constantly through processes powered by gravitational forces rather than internal heat sources alone. The volcanoes continue their eruptions whether anyone watches or not. The plumes rise and fall in cycles, governed by physics rather than observation, and the surface renews itself on timescales that erase history as fast as it can be written. Io is eternal activity. The 400 or more active volcanoes distributed across Io's surface represent a concentration of geological activity unmatched anywhere else we have discovered through all our exploration of the solar system to date. Earth possesses perhaps 1,500 volcanoes that have erupted in the past 10,000 years, but only about 50 that erupt in any given year, on average across our much larger planet. Io maintains hundreds of active volcanoes simultaneously on a body smaller than Earth's moon, each one powered by the same tidal heating mechanism, extracting energy from Jupiter's gravity. The scale is remarkable. The heat flowing through Io exceeds what Earth produces, despite the enormous size difference between the two bodies. Energy converted from gravitational flexing into thermal output at rates sustained for billions of years continuously. This heat keeps the interior molten, feeds the volcanic activity, drives the surface renewal, and shapes everything about this moon's character that makes it extraordinary among all the worlds we know. The energy comes from outside, from Jupiter, from the orbital relationship that Laplace described mathematically before anyone knew volcanoes existed on this distant moon. External forces create internal fire. The surface colors that first caught our attention when we approached this world reflect the complex chemistry of sulfur responding to the temperature variations that volcanic activity creates across the terrain continuously. Yellow and white where cold, orange and red where warmer, dark where silicate lava has recently emerged, before sulfur coatings can accumulate over fresh surfaces, exposed to the volcanic conditions present everywhere. The palette is painted by temperature and chemistry acting together, a world decorated by its own activity rather than by any external artistic intent whatsoever. Beauty emerges from physics. The plumes that rise hundreds of kilometers above the surface carry material that eventually falls back to coat the terrain in deposits that contribute to the surface renewal, erasing all impact craters from the geological record continuously. These fountains of gas and particles represent the explosive side of Io's volcanism, complementing the quieter lava lakes and flow fields that constitute the effusive activity happening simultaneously across this hyperactive world. Both styles of volcanism operate at scales that dwarf anything comparable on Earth, both powered by the same tidal heating, both contributing to the constant transformation that defines this moon's existence. The surface lives. The orbital resonance with Europa and Ganymede maintains the conditions necessary for all of this activity to continue indefinitely into the future, without the decay that would otherwise stop the tidal heating over time. The outer moons pull on Io at regular intervals, keeping its orbit elliptical, ensuring that the gravitational flexing continues, guaranteeing that the heat keeps flowing and the volcanoes keep erupting for as long as the Jupiter system persists around our Sun. The mathematics of orbital mechanics sustain the geology of volcanic activity through connections invisible but unbreakable. Binding these moons together, gravity maintains fire. The radiation environment that makes Io hostile to spacecraft and impossible for biological life adds another dimension to this moon's extreme character beyond the volcanic activity alone. Jupiter's magnetosphere bathes Io in energetic particles that would be lethal to humans in minutes, creating conditions that require us to observe from distance using robotic eyes protected against the harsh particle environment, present continuously at this orbital distance. We cannot visit Io directly, cannot walk across its sulfur plains or peer into its lava lakes with our own eyes, can only watch from spacecraft, designed to survive what we could not. Distance protects and separates. The future holds continued volcanic activity for as long as the orbital conditions persist that drive the tidal heating responsible for everything we have observed during this exploration across Io's remarkable surface. Billions of years from now, assuming the Jupiter system remains intact, Io will still be erupting, still renewing its surface, still turning itself inside out through the continuous cycling of material from interior to surface and back again repeatedly. The process has no endpoint built into its physics, no reservoir being depleted, no timer counting down towards cessation of activity. The furnace burns eternal. Missions planned for the coming decades will return to Jupiter and its moons with instruments more capable than any that have observed Io previously during earlier exploration campaigns. The Io Volcano Observer concept would study this moon from closer distances for longer periods than any previous spacecraft has achieved near this radiation-hostile environment successfully. New observations will reveal details we cannot currently see, answer questions we have not yet thought to ask, and likely raise new puzzles that future generations of scientists will work to understand in their turn. The exploration continues. The view of Io from departing distance shows the moon as a mottled sphere of impossible colors, hanging against a black backdrop of space, with Jupiter's bulk visible beyond. The setting we first encountered when approaching this world at the beginning of our journey together. The colors seem more meaningful now. Each yellow and red and orange region representing processes we have come to understand through patient exploration of individual features and underlying mechanisms operating continuously across this restless surface. The moon is smaller in the view now, receding, but the knowledge of what it contains remains present. Understanding changes everything. Io continues its orbit as we watch from increasing distance. The volcanic activity ongoing whether observed or not, the plumes rising, the lava lakes overturning, the surface renewing itself through processes that began before life existed on Earth and will continue long after our sun has exhausted its fuel and died. This small moon demonstrates what geological activity can look like when powered by external forces rather than internal heat. What volcanism means when operating without pause for billions of years. What a world becomes when it truly never rests from its own transformation. Io is activity incarnate. The distance grows, Io becoming just another point of light among the moons of Jupiter, visible from across the solar system, indistinguishable from this range. Despite all the fire and color and activity we know continues on its surface, invisible to distant observation. Jupiter dominates the view now, as it dominates everything in its system gravitationally. The giant planet that creates the conditions for Io's volcanism through the tidal forces that keep its smallest Galilean moon molten and active continuously forever. The relationship defines everything we have seen during this exploration journey. Giant and moon remain connected. Sleep comes easily after journeys through such distant places, the mind settling into rest as naturally as Io settles into patterns of activity that have continued without change for longer than the Earth has existed as a solid world orbiting our sun. The volcanoes burn on through the night, whether anyone watches or remembers or dreams of sulfur plains and lava lakes and plumes rising into the black sky above a world that never stops transforming itself in the light of a giant planet that never sets from its most active moon. The eternal furnace burns on, and rest finds those who have watched from afar, and both are part of the same universe, continuing its existence in all the ways it knows. The night continues, and so does Io.